Hello everyone, I'm Krishantan Sundararaja from Purdue University. Today I'm going to talk about our work HACCLE Metaprogramming for Secure Multi-Party Computation. This work is done in collaboration with many people from Purdue University and Raspberry Labs. My co-author Yuyan equally contributed to this work as myself, and this was done while she was at Purdue University. Now let us look at secure multi-party computation. Secure multi-party computation is a collection of cryptographic techniques that enable multiple distrusting parties to jointly perform computation without revealing any participant's private data, the data they do not wish to make public, generally abbreviated as secure MPC. There are many practical applications such as secure online auctions, privacy-preserving machine learning where model and data are owned by different parties, privacy-preserving genomics, spam filtering on encrypted emails, etc. There are many different secure MPC protocols, and they are based on cryptographic techniques such as secret sharing, homomorphic encryption, and gobble circuits. Each protocol requires the parties to obey a particular communication model. For example, client-server model, where there are only two parties. Different application setting and protocol together may have different trust models of the parties. For instance, a semi-honest trust model is where no party can deviate from the protocol when performing the computation, but some parties may try to actively learn details about other parties. So you can see the secure MPC application setup is inherently complicated, and now let us see a motivating example to understand why it is challenging. Let us consider an example of auction where parties do not trust each other, even the auctioneer. Example, public procurement for building contracts. All parties place their seal bids. The winner is the party who offers the highest price for the item, and it is sold for the winner for that highest price. This is called a first price auction. It requires few comparisons. But in order to avoid price discovery, the winner is offered to buy the item for the second highest price. This is known as the second price auction, and the computations are different. Now think of a scenario where there are multiple items and contract terms that considered when comparing bids for these items. This is generalized auction. It would become cumbersome to write each auction separately. Secure MPC applications are already difficult to implement. If we have an approach that would automatically specialize a generalized auction to second price auction or to a first price auction based on the scenario, then that will make the development of secure MPC applications much smoother. But why do we need a compilation framework to solve this problem? First, secure MPC applications are extremely slow because of the nature of cryptographic primitives. Even switching from one backend to another backend, which uses the same protocol, requires enormous effort since the abstractions provided by the backends vary. Some provide primitive abstractions such as arithmetic operations, and some provides their own higher-level abstraction to express your computation. Migrating your computation from one protocol to another requires some level of cryptographic expertise. Since secure MPC applications are inherently slow, performing optimizations to improve performance is critical to get an acceptable runtime for your applications. In almost all secure MPC protocols, computations are abstracted as acyclic circuits. Hence, optimizing the circuits requires some level of circuit optimization expertise. Inspired from work in hardware design such as partial and chisel, our key approach to solve this challenge is lowering code describing secure MPC application to circuit-like abstraction and performing optimizations using metaprogramming techniques. For example, reduction can be realized as a tree reduction to allow more parallel computation. For the rest of the talk, I will discuss about this novel and compelling approach to realize secure MPC applications. Main contributions of our work are HACCLE Toolchain, a compilation framework to build and execute secure MPC applications written in Harpoon and embedded DSL in Scala based on lightweight modular staging to realize our abstractions. HACCLE Intermediate Representation, an extensible circuit-like IR to abstract cryptographic primitives used in MPC, and some optimization strategies to make the secure MPC applications performant. Now let us look at the workflow of HACCLE framework. The diagram shows all the different stages of compilation. The first stage takes a program written in Harpoon, embedded in Scala, and then it extracts the Harpoon part, which is the secure computation. After this stage, the communication channels would have been already set and the data will be ready to properly flow. Stage 2 takes in Harpoon program and translates it to an HIR program, which is the circuit-like description of the computation. At this stage, Harpoon type system prevents errors like assigning a ciphertext to plain text. Stage 3 takes in the protocol-independent HIR program and specializes it to a protocol-specific one. Type system in this stage prevents protocol-specific errors, for instance, prevent a non-player accessing shared piece of data. Stage 4 takes a protocol-specific HIR and produces code for a specific backend. We count resource estimation as a separate backend. This backend can estimate the cost of computation in a particular protocol based on a cost model. Now let us look at the Harpoon programming language, which is used to express the main secure MPC computation. Harpoon is a subset of Scala. It's an imperative monomorphic language, and it has the usual control for structures such as function calls, conditionals, loops, and recursion. Later we will see that when we lower them, functions will get inline, loops and recursions get unrolled, conditionals get lowered to a selection logic akin to a mux in hardware. Harpoon also provides cryptographic data structures such as encrypted arrays. Encrypted arrays are further lowered down the pipeline to suitable selection logic to maintain data obliviousness. We'll look into this later. Harpoon provides annotation to the ownership of a piece of data. This helps down the pipeline to type check and find any violations specific to certain protocols. Harpoon is lowered to HACCLE Intermediate Representation, which is HIR. HIR is protocol independent and it is a multi-level IR in which we can perform rewrites without leaving the IR. Not every backend provides operations on all data types. For example, a backend may provide only bitwise operations. In that case, a program written to operate on integers must be automatically rewritten to operate only on bits and bit arrays. For instance, addition of integers may be rewritten to use full adders. HIR is typed and it gets refined when it's lowered to a protocol-specific HIR program. This helps to catch errors that are specific to a protocol. Type rules provide an approximation of data access policy that specifies how data is provided, accessed, and shared. For example, code shown here shows the assertions in addition operation for the type of shared number. This gets refined with more checks when it's lowered to secret sharing protocol specific HIR. If an HIR instruction is lowered to a particular protocol in which there are no equivalent operation, that manifests as a type error. A program without privacy concerns diverts its control flow according to the input. Statements are executed conditionally, loops for a variable number of iterations, etc. To protect privacy, Boolean and arithmetic circuits must be oblivious in the sense that they perform same sequence of operation regardless of the input. This requires indexing an array with the ciphertext is encoded as a huge multiplexer circuit. If the condition of the if-then statement depends on a ciphertext, then it is transformed to a selector logic. All function calls are inlined, all loops are unfolded as the number of iterations is a compile time constant. For recursive functions, obliviousness is achieved by using an extra plain text parameter that gives the bound of the recursion. This helps to make sure that the recursive call only iterates the number of times specified by the bound. Now let us look at an example of Harpoon and equivalent HIR program. On the left, we can see a textbook implementation of the greatest common divisor GCD computation in Scala. In the middle, we can see the GCD implementation in Harpoon. For simplicity, the input values are shown to be constants. You can see Harpoon code is not too different from Scala code except for some special annotations. The annotations express that a user Alice computes the GCD of a private data A and B through a different party which performs the computation on the data in an encrypted form and provides the encrypted results to Alice. Please note that the bound annotation, which is a compile time constant. The right one shows the corresponding HIR program. The translated GCD function has one extra parameter d initialized by the bound Harpoon annotation and decreases with each iteration. Note that the function func is a polymorphic overloading function in HIR. Now let us look at two optimization strategies to improve the performance of secure MPC applications. The multiplicative depth of the circuit is the main practical limitation in performing computations over encrypted data. In computations, we can eliminate multiplications if one of the operand is plain text and it has the value of 0 or 1. In addition to that, by grouping computations, we can reduce the multiplications and depth of the circuit. For instance, let's compute the 8th power of an encrypted number. The code is shown on the left represents this computation. If we translate this naively, we may end up with 7 multiplications, but by grouping these computations, we can accomplish with only 3 multiplications. The abstract circuits are shown on the right. Next optimization strategy is being clever in comparing private values. A particular private comparison can be encoded into a set of operations based on what's offered by the backend. Some of them can be faster than others. For instance, greater than or equal to comparison can be either rewritten to a less than operation and an equal to check, or less than operation and a subtraction operation. In this case, later is faster. We have evaluated our approach for developing secure MPC applications with 3 case studies: secure auctions, matrix vector product, and merge sort. We will investigate these case studies in detail next. Secure auction is our motivating example. On the left, we have shown the imperative style implementation of second price auction. Our compiler can transform this code into a simpler functional style 1, shown on the right. This yields a circuit of logarithmic depths that allow efficient parallel computation instead of the one with a linear depth. Our next case study is a matrix vector product. Matrix vector product is a co-kernel in privacy-preserving machine learning applications such as secure NN. In this setting, one party owns the matrix and the other party owns the vector. The Harpoon code for matrix vector product is shown on the left. We have applied scalar multiplication optimization that we saw earlier for this case study. We can clearly see the performance enhancement when we increase the matrix size. Our third case study is merge sort implementation in HIR. Secure sort is a core kernel in anonymous messaging applications. This implementation requires language features such as array index, conditionals, and recursion. Notably, an array lookup on a private index is not supported by most programming languages. In conclusion, secure MPC applications solve practically important problems, and developing secure MPC applications with reasonable performance requires expertise from a variety of fields. In this work, we have come up with the HACCLE toolchain, which offers a compelling approach to the design and implementation of secure MPC applications using metaprogramming techniques. Thanks for listening to my talk, and I'm happy to take any questions.